Hi, I'm Gemma Sherwood. I'm the Senior Lead Practitioner for Mathematics across the Ormiston Academies Trust, and today I'd like to talk a little bit about probability in school. So the first thing I wanted to consider when I was wondering where to start on this really important, quite large topic was why it's important. Why is it that we teach this on our school curriculum? Why is it given such fundamental place on our school curriculum? And the best quote I found to summarise this was from a paper by Batanero et al. And I've got the reference at the end of the PowerPoint for you if you want to look it up. It's a research summary actually, and they said that to adequately function in society, citizens need to overcome their deterministic thinking. That's thinking that everything has a cause rather than things being down to chance. And they need to accept the existence of fundamental chance in nature. At the same time, they need to acquire strategies and ways of reasoning that help them in making adequate decisions in everyday and professional situations where chance is present. So thinking about this, we live in a world full of data, so discussions of risk and analysis of multiple options in different scenarios in which we find ourselves. This happens everywhere in the world, every day. So an understanding of probability and the ability to criticise and discern what people are saying in these kinds of discussions is really imperative. Let's stop to consider for a moment what probability is. You might think this is an obvious question, but there are quite a few issues around it that it's worth exploring briefly. Our reality is really messy. It's unpredictable, particularly on a micro level. I do not know what is about to happen in the next second. If I were to roll a dice now, I would not know what would happen and what number it would show. But our reality can be more predictable on a macro level. So if I were to roll the dice multiple times, I do know that it would have a propensity to show each of the numbers approximately 1/6 of the time. Tony Gardner, in his book on teaching mathematics at the secondary level, said that we can view probability as what happens when, first of all, we take single inadequate glances at something, and these single inadequate glances show us precious little, the kind of shadows of reality, if you like. But if we take multiple glances, each of them in itself inadequate, but then we put them together, this can approximate a picture of reality. It kind of gives us a window through to what's really happening, even though we can still never predict it, still never know what's going to happen on the next roll of the dice, for instance. So probability is a way of us attempting to structure reality by recognising that some predictability does exist and that we can approach some model of reality on a large scale. Probabilistic reasoning helps us to search for signals in noisy processes. I like this metaphor because this communicates to me really clearly the fact that we have this messy reality, that's our noisy processes, but within it we can see some clarity if we step back and look on this larger scale. The probability theory, the mathematics that mathematicians do, contains within it several views of the definition of probability itself. So the classical view of probability, which it kind of started to be worked on in the 16th century, but mainly in the 17th century by Fermat and Pascal, followed by de Moivre in the Doctrine of Chances. This is generally considered to be the first textbook on probability. This was in 1718, and he defined probability in that classical way with a fraction, saying that we're talking about the favourable outcome over all possible outcomes. But he worked in a very limited number of cases. So he worked with basic events, generally a pass-fail, like throwing a coin, heads and tails. And he worked with equiprobable events, so things like rolling a dice where each outcome has an equal probability. So of course there are limited applications to that. In the 18th century, Bernoulli worked on the law of large numbers. This is what we mentioned before about how if we repeat an experiment over and over and over again, we see that some kind of convergence happens, some kind of limit is approached when we work out the relative frequency of each outcome. So the frequentist view of probability defines probability as the limit of the relative frequencies as the number of trials tends to infinity. So it's kind of approaching probability from an experimental, that's the a posteriori in the table there, an experimental angle rather than from a logical angle. In the 20th century, there was a lot more work done on probability, particularly as the data around us became more readily available, easier to collect, larger in terms of data sets. So Popper, I think it was in the 1950s, but I'll double check that, he said that a random system has a tendency to behave in a certain way, and he called this propensity. And I mentioned that before with the dice, the fact that if I roll a dice multiple times, it has a propensity to show me each number a sixth of the time. But that still doesn't mean that it's going to do something in each individual trial. Keynes and Carnap in the 20th century also took the classical idea of probability and started to extend it to multiple outcomes, so not just pass and fail like de Moivre did, but also unequal probabilities as well. So they really extended the scope of our understanding of probability here. It's worth noting that what we currently do with probability is really recent in terms of the whole history of mathematics, as you can see from this. And then finally, reveal both at the same time, computer froze. Finally, we have in the 18th century, Bayes, as in Bayes' theorem, he worked on the idea of subjective probability or conditional probability. So this is the idea that a probability is never constant because it can change depending on other things that have happened. Bayes' theorem, of course, is the one that we use at A-level with a probability of A given B, and we have the formula for it there. And then later on in the 20th century, Kolmogorov, Russian mathematician, who's generally considered to be the last mathematician who was able to study all areas of mathematics, because after him it just became too large. Kolmogorov set out the formal definitions of probability that we use today, and the axioms, that's the rules that underpin probability, the things that we take to be self-evident. So things like the fact that all probabilities must be between 0 and 1, and the probability of the set of all outcomes is equal to 1, and things like if A and B are mutually exclusive, then the probability of A and B is just the sum of each of their individual probabilities. These axioms set out formally was done by Kolmogorov. So we've got these different ways of approaching probability, and you'll probably, if you look down that table, address each of those different ways at different points for the different classes. I think we spend most time on the classical and logical ideas of probability, a bit on the frequentist idea, and when we get perhaps up to A-level, we're a little bit more axiomatic, we're a little bit more formal with it, and we also look in more detail at the subjective approach to probability and conditional probability there. The other thing to consider is where probability sits within the wider domain of mathematics. There are some people who say that statistics and probability are separate to mathematics, which is mainly number, algebra, geometry, but obviously we can't escape the fact that probability and statistics use mathematics exceptionally heavily, and they wouldn't exist without mathematics. So it uses the mathematics of number and algebra, particularly our ideas of proportionality with fractions, decimals, percentages, but it is fundamentally different from the mathematics of number and algebra because mathematics is a logical domain. We can deduce things precisely, we can prove things mathematically. So most mathematics kind of fits in this broad idea of it obeys rules. Probability, however, is different because it's an attempt to measure or predict or analyse things that are unpredictable, things that are changing, things that are random. It doesn't obey rules. Now, we know we can see that we've got tendencies and propensities there, but like we said before, we can never say what's going to happen next. So it's different to mathematics, although it borrows from mathematics. So it uses elements of mathematics to try and analyse this messy world that we live in. So in probability itself, we use mathematical tools such as numbers to try and describe or explain uncertain events in some way, to try and model and predict randomness, to try and assess the ideas of fairness and bias. As well as our numerical tools, we have our graphical tools as well at our disposal to try and help us organise our thoughts and to represent what we want to do more clearly. And probability contains these different but related ideas that we have to tackle, the ones that we saw in the table on the previous slide, different related ideas to tackle but under the same title, this title of probability, and the same axiomatic framework. We spoke about that being developed in the 20th century. So we have experimental probability, which comes under those frequentist and subjective titles or views, if you like, and we have theoretical probability, which comes under the classical, logical and also subjective views. So in school we tend to split it, don't we, into experimental probability and theoretical probability, and they are both quite different but so related, and this is where I want to focus part of this presentation now, is on the idea of experimental and theoretical and how they're related and how we can exploit those relations probably a bit better than we currently do. I say we because I'm kind of drawing on my own experience and working with lots of other teachers. I hope you find it useful. So the one thing I want to do then before we go on to some more of these ideas is think about the probability specifically on the school curriculum. It fits under the banner of statistics and probability, and I like to think of them as two sides of the same coin. So in statistics we observe and record data and try to find models that fit them. But with probability, we take a model, the probability model, and we use it to help us think about what we're observing. So stats starts with the observations and then takes them and finds a model to fit. Probability starts with a model and uses it to help us analyse the observations. This is the content of the school curriculum at Key Stages 3 and 4 in England. So this is taken directly from the national curriculum here. We've got a few areas, and I've deliberately highlighted them now to kind of draw out the links between them. So here then you can see the links between Key Stage 3 and 4 when we're talking about, in Key Stage 3, frequency of outcomes, probability experiments, fairness, the probability scale. But in Key Stage 4 it gets a little bit more advanced because we're talking about predicting future outcomes using probability models. Notice that the vocabulary here, although it's talking about a similar thing, is more advanced. So we're talking about empirical, unbiased samples, tending towards theoretical probability distributions with increasing sample size. I've then grouped these two together, which are basically the same, but again, one uses more complex language. And then these two, this talks about sets, Venn diagrams, sample spaces, and then the same in Key Stage 4 as well, but bringing in also conditional probability in Key Stage 4. So in terms of those views of probability from probability theory itself, we've got the frequentist and classical views. So that's our experimental and theoretical probability essentially, with a bit of logical, as in starting to be a bit more formal in Key Stage 3. They're all extended, and we bring in some of the more formal axioms and the idea of subjective probability added. So we have quite a few challenges that we are faced with when we're teaching probability, as well as misconceptions and preconceptions that pupils come to us with. We've got the idea of the multivariate nature of probability. When we teach experimental versus theoretical probability, are we clear with pupils on how these things are the same and how, as well as how they are different? We've got the idea of randomness. Are we communicating this idea of lack of predictability, but also predictability coming from it, especially with the law of large numbers? Are we clear that probability is different to the other mathematics they've studied, even though it uses things that are familiar to them, such as fractions and decimals? We have the idea of counterintuitivity here. Lots of probability can be counterintuitive. The classic example there is the gambler's fallacy. The gambler's fallacy says that if I were to roll a dice 4 times in a row, I get the number 5. I might be tempted to think that the dice is therefore more likely to show a 5 on the next roll. Now, we know from probability theory that if this is an unbiased dice, then that's not the case. And what happened to me with the 4 5s in a row was very unlikely, but it still happened. But that's the gambler's fallacy, and it is counterintuitive. However, intuition can be really useful. Our pupils come to us with a lot of intuition about areas of probability just because of their experience in life. And this can help us because it gives us something, it gives us a grounding to work from. So things like comparison of likelihoods. There is research that shows that pupils are very good at comparing the likelihood of two things, saying whether something is more or less likely than something else without really having to be taught it. They also have a good understanding of fairness and bias, particularly if they have siblings and you're trying to share out the chocolate cake. However, this intuition can become problematic when it conflicts with mathematical theory, when it's a wrong intuition, as we saw with the gambler's fallacy. But there's also things such as survivorship bias. So a good example of survivorship bias is every year there are certain famous people around exam time who put out tweets that say, "Don't worry if you didn't pass your A-levels, I didn't get my A-levels, and look at me, I'm a millionaire." And it's kind of suggesting that therefore it's okay for other people not to pass their A-levels. That's survivorship bias. It's saying that because it happened to happen well for me, it's going to therefore happen well for everybody else, and that we obviously know that's not the case. It's also confirmation bias, which we humans are awfully susceptible to, which is where we automatically filter out things that disagree with our worldview or what we think. And other logical fallacies. So it's very important that we tackle these head on, particularly, and you will see them come up in lessons on probability. There's also this, that we mentioned before, this deterministic view of the world, the fact that we have a tendency to search for a cause in everything. And we're not very good at dealing with the idea of randomness and chance and the fact that something just happened. Our intuition tends to provide a relational understanding. This is what I mentioned just before about how children are very good at comparing whether two things are more or less likely than each other. It's not very good at providing proportional understanding. So the idea of assigning a number to a probability or a chance, that's not intuitive, that's mathematical, and that's something that therefore needs a lot of work if we want all of our pupils to really get their heads around this. We also find that our pupils can have an immature understanding of chance and possibility, kind of linked to what we were mentioning before. An example of that, I've had this one before. A student has said to me, "Miss, my phone says that there's a 65% chance of rain right now, but look, it's not raining, so my phone must be wrong." And that's an immature understanding of this idea of chance and possibility. The fact that it says 65% and I'm guessing they're thinking it's more than half, therefore it must be happening now. We also have assumptions of equiprobability of outcomes. You will definitely encounter this if you haven't already. There are 5 outcomes, so therefore each of them must have a probability of 1/5, because there are cases where pupils assume that the number of outcomes automatically determines the probability because those outcomes are equiprobable. We also have the idea of conflation of events that can be assigned a numerical value with those that are more just ideas. So let me explain this a bit better. Let's say, for instance, that we asking students, what's the probability or what's the chance that the world will end tomorrow, or what's the chance that a dinosaur will fall out of the sky? What we mean there is it's impossible, it's not going to happen. But you've always got that student who goes, well, it could happen, this, it could do. And the reason you then get into silly discussions about whether it could or couldn't, and you feel sometimes like things get derailed, I think is because what we're doing is we're taking something that we can't assign a numerical value to, and we're trying to assign a numerical value to it, especially when these form parts of discussions around a probability scale, which we'll talk about later on. So we have to be very careful about the types of examples that we use. There's also lots of complex language in probability. Some of the words are unfamiliar. Some of them can be false friends. So the idea of an experiment in probability is different to the idea of an experiment in science. Outcomes and events and the conflation or the confusion of those two words. So we have to be very careful about the language we use, and just like everything we do, we have to teach the language explicitly and carefully and use it at every opportunity and give our pupils opportunity to use it as well. So I think there are two general approaches to a sequence of teaching probability. I'm just going to focus on Key Stage 3 for now. And the first one is the idea of what I'm calling the specific to the general. Let me explain this a little bit more before I show you the sequence. So experimental probability encompasses the idea of relative frequency and the law of large numbers, and we've seen from the frequentist view of probability theory that probability in that view is defined as the limit of the relative frequencies as the number of trials tends towards infinity. So the idea of experimental probability and relative frequency, I'm calling it general because it applies to many more scenarios than the specific theoretical probability that we study in school does. The specific theoretical probability is things like dice and coins and those kinds of things. And of course there are more examples that we can use there, but relative frequency can be applied in any scenario because you can do an experiment on anything. So that's a little bit more general. That's where I'm going with that. And I think lots of people in schools, based on my experience, teach with the specific first, the theoretical ideas first, and then maybe move up to the more general and the idea of experimental probability afterwards. So it might look something like this, starting with the classical definition with fractions, applying it to multiple scenarios, practicing it in lots of different ways. Getting a little bit of a more formal mathematical definition of probability, then thinking about equiprobable outcomes, introducing this idea of summing to one. Somewhere in there, there'll be a probability scale as well. So we're looking at the limits of the proportion that we assign to probability. And we can look at different probabilities, as in not equiprobable outcomes, and see that the sum to one still holds. We look at more complex experiments, more complex outcomes, trees and tables, those kinds of things, and sample spaces. And at some point in there, we bring in the idea of relative frequency and we do some probability experiments and we show that it approximates theoretical probability. And of course, somewhere in there as well, we have Venns and sets, and we kind of go out to a wider domain and introduce more logical ideas. Now, this specific to general approach has some benefits. So we start off by linking our new study of probability to existing mathematical knowledge of fractions and decimals and percentages, and that happens from the outset. And because we bring in these formal mathematical ideas from the start, we potentially have more time to practice them in our finite, limited length of our unit, however long it may be. But there are some really clear risks with this approach as well. One of them is this: we're applying a theory without understanding of the underlying concepts. What I mean by this is this concept of the messy world and the fact that probability is a way of trying to describe a messy world. When we start with the classical definition of probability, we don't really communicate that. So I'm not convinced how well this approach communicates the reason for probability and the reason for probability theory. The other thing in there as well is that it doesn't really motivate the need for relative frequency. So if you've spent a lot of time on classical probability and theoretical probability, and then you do some experiments, and I guess the classic experiment is throwing a coin in the classroom, and the pupils end up working out the relative frequencies and see that they approximate to 0.5, you can kind of see why they might go, but I knew that anyway, so what's the point in this experiment? And I can see why they would come to such a conclusion, because it's not telling them something they didn't already know, and they couldn't already work out much quicker without having to do all of that. So that's quite a clear risk when we're dealing with, when we're teaching in that. So the other option then is, instead of teaching from the specific to the general, we could teach from the general to the specific. And it might look something like this. We would start with some informal experiments. What's happening? Can you predict what will happen next time? Why not? I'm going to go into some more detail on this later on. It helps us to gain a conception of unpredictability and randomness and what a slippery thing reality really is. It allows us then to start thinking about recording outcomes and their frequency. It motivates the idea of relative frequency, so that because it enables us just to compare experiments of different sizes, and we start to see that this relative frequency number is very consistent between everybody. And we start to see the limits of this relative frequency number, from nothing happening to something happening all the time. So from 0 to 100%, which motivates the idea of the probability scale from 0 to 1. It then allows us to bring in this idea of theoretical probability as a quicker way of getting the relative frequency in certain circumstances. So if I'm throwing a coin, I don't need to throw it 50 times. I can just go, two outcomes that are equally likely, therefore the probability is a half. In that, of course, we've got, just as before, recording in more complex ways, more complex experiments using tables and trees and those kinds of things, and sample space diagrams and Venns and sets in there as well. So it's not necessarily a particular, all of it in that order exactly, but that's the broad order of things that the general to specific. There are benefits and risks to this approach, just like the other one. The benefits are the fact that it focuses on the underpinning ideas of randomness and unpredictability much more. It communicates them more clearly because you're thinking about them before you start to think about probability. So it puts probability in that context. It also gives a motivation for theoretical probability in that it's easier in certain cases. Don't need to do 50 trials throwing a coin because I can use the theory to get to the probability, but I also understand that that's not possible in every case, and therefore I have relative frequency as an alternative. It also motivates the 0 to 1 scale in that it gives me a reason why it's 0 and 1, because something can happen never or 100% of the time, and I see that in my experiments. The risks associated with it are particularly that the ideas can get lost in the experimentation. If you're spending lots of time in the classroom doing physical experiments, then your pupils can get hung up on the mechanics of what they're doing at the expense of the ideas you want them to learn. There are ways around this because you can use technology. There are websites that allow you to generate large data sets by doing these trials in a very short space of time. So you can do this without doing it physically, but there is a lot of benefits doing it physically if you manage it well. And of course we have this idea, just like before, of limited curriculum time. So you have to be careful that you don't prioritise this idea of experimentation and understanding randomness and understanding unpredictability at the expense of practising formal ideas of probability. There are pros and cons to both approaches, whether you go specific to general or general to specific. And there's discussion to be had around which approach might benefit your pupils more. But have the discussion. It's a really good one, it's a really useful one. And as with everything we teach in mathematics, there's not necessarily a right or a wrong way to do it, but some ways will draw out some ideas more than other ways. And it's all about where you think your pupils need to focus, where their attention needs to be, and that will determine some of the decisions that you make. Notice how in both approaches I didn't start with a 0 to 1 scale. Now I've said that because it's really commonplace in my experience for people to start teaching probability with the scale. And I'm going to talk in a bit about why I think that's not necessarily the right thing. So before I do, I want to consider that we've looked now at two worlds. There is the real world of messy data, the one that our pupils inhabit before they come to our lessons on probability. There is also then the mathematical world of theoretical probability that we want them to leave our lessons understanding. But these two are quite separate, and the gap between them can seem very large. the point of probability is to try to make some sense of the real world of mess and intuition, but how probability makes sense of it is not obvious to all pupils. And that's where our job comes in as the teacher, in designing sequences of learning that get them from one world to the other so that they can use the mathematical world to help them understand the first one. Tony Gardner, in the book I mentioned before, talks about the way that we can move our pupils from one of these worlds to the other using controlled data. So I'm thinking of this as a bridge between the two worlds now. And controlled data summarises all the things we do in the classroom and the experiments we choose and the examples we use and the activities and tasks we give our pupils that are very deliberately selected to take them from their understanding of the real world and messy data across to an understanding of the mathematical world. So Gardner recommends using examples and experiments with finitely many outcomes, which is quite commonplace in classrooms, and symmetry that make outcomes equally likely, because then work becomes an exercise in counting and it makes it easy to work with. In doing this, the idea is that we make the theoretical world apparent. We draw ourselves along from the real world to the theoretical world in a seemingly logical way. It also gives the mathematical or theoretical world a clear purpose in helping us to analyse the real world, and it keeps its link to the real world because we're able to go back along the bridge in the future. So our pupils start in the real world of messy data. That's how they come to us. So let's build on their experience and their intuition and keep it quite informal. So we could have discussions along the lines of, what will the weather be like tomorrow? How do we know? What's the most likely month to be born in? We're then going to move on to things, we're moving on to the bridge, this controlled data bridge. We're going to move on to things that can be tested in class. Keeping it really informal. It's the most likely month to be born in, see what people think. But then you can ask the class and see whether or not there is one that's more likely than others. And then you can ask them whether or not other classes might see the same thing. How many pets can we expect someone to have? What do we think? Let's ask the class. Let's gather a bit of data here about it. And then move on to things that can really be enumerated, but still keeping it informal at first. If I throw this coin 20, 30, 40 times, how many tails will I expect to see? How many heads will I expect to see? Did your partner get the same number? You can either do this physically or, like I said before, you can use technology to show it on screen. You can use proportion here now as a way of comparing sets of different sizes. So so-and-so rolled it 20 times, so-and-so managed to roll it 50. So let's compare the percentage of heads that each of you got. This is the idea of the relative frequency, and it's only at this stage that we can start to introduce terms for this. But one experiment is not enough to draw out the idea of relative frequency. You need to have a selection of experiments, all with equiprobable outcomes, so not just, say, rolling a coin, and you need to look for something that all of these experiments have in common. And after you've done enough of them, your pupils will see that every time we do one of these experiments, the thing we're measuring the frequency of, or the proportion of, always seems to tend towards a limit. And when they see that enough times, they will then understand what the relative frequency is. You can then explore the limits of this proportion, the fact that it goes from nothing up to 100% or 0 to 1, which motivates the probability scale. Don't be fooled that the probability scale is easy. I think a lot of people start with it because it seems like probably the easiest idea in probability, because you're just going, there's 0, there's 1, and it's kind of a number line, and we've seen number lines since primary school. But there are all sorts of places where this can confuse our pupils. I think one of the problems here is if this is a typical example that I have done something like this in the past, and I've seen it plenty of times before. we are mixing here things like what's the probability it will rain next week and what's the probability it will rain tomorrow, which of course will vary depending on what time of year we're in, with what's the probability that a coin will land on tails, or what's the probability that the spinner will land on a 4 if I show them a spinner. The problem there is the fact that we're mixing things that we can enumerate with things that we cannot enumerate. So this idea of making comparisons between probabilities becomes really difficult, and it makes this exercise much harder than we intend it to be. If, however, I remove those ones that I grayed out there, those are the ones that can be enumerated, those remaining ones, the probability a baby will be born today, the probability that I will win Wimbledon this summer, obviously that's not going to happen. Notice I've also removed the 0 and 1 from the end of the scale. So this is now just an exercise in comparative likelihood, and that's relatively straightforward. So we can start with this idea of comparative likelihood before we then bring in numbers, and I'll show you that in a bit. So this is what we had on before, exploring the limits of the proportion. Now we've reached this point, I think we're probably ready to start working properly in the mathematical world, because we've taken people's experience of the messy real world, drawn them along through to the theoretical side of the math. So we're now here, we're in the mathematical world of theoretical probability. And we can start to really talk about the numbers now. We can talk about proportions, fractions, decimals, percentages. We can be really explicit about these now and spend time on them in the knowledge that we have taken pupils from the messy world where they started off with their own experience, and we've moved them through and gradually narrowed this experience down to a place where we've motivated the mathematical world of theoretical probability. There, of course, are going to be obstacles if pupils have struggles with these numbers, fractions, decimals, percentages, or the fact that they're equivalent. But this is where we can spend a bit more time on them. So now we've got the probability scale back, but I have limits on it. I have 0 and 1, and I'm not going to be dealing with items that are not enumerable. What I'm using now are these 3 here, which I can assign a number to. So now I can start to do comparison of likelihood with numbers as well. So I'm hoping this is clear that there is that extra layer of complexity, because comparison of likelihood without numbers is much easier, because you haven't got to think about the relative size of these numbers. Some pupils will find it very easy, some pupils will not. The world of theoretical probability in school maths is quite small, remarkably small, because it's very connected, and it can feel disconnected to our pupils if we teach lots of things in lots of different ways and if we teach them as separate ideas. But hopefully I've started to show how we can use our teaching to draw pupils along the journey. And we need to then think about how we do that when we're in the mathematical world itself. So in this mathematical world, we've already spoken about these idea of proportions, and we've mentioned briefly about the fact that we have lots of diagrams that we can use to help us in our thinking. There are lots of obstacles here, especially with these representations that help us with probability, these diagrams. I think a lot of the time our pupils don't necessarily see how lots of these diagrams can be equivalent. They see them as very separate things. We also have the idea that tree diagrams can be exceptionally hard to grasp, and if you've been teaching a while you will have seen this. So one way is to introduce tree diagrams in comparison with something that pupils have already met, like a two-way table. So let's look at this question for an example. 2 coins are thrown. We want to list all the possible outcomes, so that's the sample space, and then find the probability of throwing 2 tails. Now, if you just ask people to list all the outcomes, that can be quite difficult. However, if they are able to draw some kind of diagram, like a two-way table, in this case it's a non-numerical two-way table of course, then this sample space diagram helps them to make sure they have an exhaustive list. But this diagram can also help us to see how a tree diagram works as well, because you could do a tree diagram for this. I think I would probably argue that it's a little bit harder to do a tree diagram for this one, but it still could work. Pupils often find it hard to draw an accurate tree diagram, as we know, so they could probably do with another bridge from the two-way table to the tree diagram, something in the gap there between them both. So let's illustrate this with a different question. Here's our second question. A bag contains 3 red balls and 4 blue ones. 2 balls are taken at random, and what's the probability of taking 2 of the same colour? Now, let's look at our table at the same vein as it was before with the coins. This diagram is no longer so useful, and it's worth pondering for a second why this is not so useful. I mean, this diagram suggests to us that the probability of 2 reds is a quarter and the probability of 2 blues is a quarter. And the mistake is that in this diagram, we are not accounting for the fact that we have different numbers of red and blue balls. So a two-way table might look like that, and you can see that the leading diagonal has been blanked out because you can't take the first red ball followed by the second red ball again because you've already taken it. So we have this idea of conditionality there as well. But that's a big, unwieldy table. I mean, it's nothing wrong with it, but it's not necessarily the clearest. So let's have a look at this. This is from Don Stewart, and this is a root diagram. It looks a bit like a tree diagram, doesn't it? And you can see that we have 3 red branches, first of all, and 4 blue ones. So each of those represents a red ball being chosen or a blue ball being chosen. And then if you notice on the second set of branches in the top, our 3 red lines become 2 red lines. And that's saying if we've chosen a red ball, then of one of those 3, there will only be 2 left to choose from. So this root diagram conveys this idea of conditionality really beautifully, and it also shows us why we multiply along the branches of a tree diagram too, because we can see the number of possible ways of getting from the start to the end along each section of the diagram. That then leads us beautifully into a tree diagram. So something like this root diagram could be a very useful way to help pupils make sense of a tree diagram, to help them draw it more accurately and to understand the numbers that they are writing on the tree diagram. And the great thing about the tree diagram at the end is the fact that it encompasses all the information from the root diagram, but it's much easier to draw when you understand what you're doing. Now, there are other types of probability questions where other diagrams might be more useful. So let's have a look at this one. We've got 120 students in years 10 and 11, some take French, some German, and then we've got some information there about the ones who take French and German in different year groups, with a question about the probability of a year 11 student taking German. So this is the kind of question that lends itself really beautifully to a two-way table, and I've filled into the table there the information from the question. But you can also do a frequency tree for this. And this is another time where it's tempting to teach something like frequency trees separately to something like two-way tables, but they are one and the same thing, just a different way of visualising the information. And it's helpful for our pupils to see both of them so that they can make those links. Here's another question for you. This time we're still looking at French and German, but it's only year 10, not year 11 as well, like the previous one. So we've got 65 students in year 10, choosing up to 1 language, 30 choose French, 3 study none, and the rest choose German, and then we have a probability question at the end. Now, we could still do a two-way table, but it would look something like this. It's a little bit... It's not particularly necessary. I mean, you could probably answer the question without it, really. But what I like about drawing a table there is the fact that it shows that this is still possible, even with the information that we have. So it helps students to see that these things are not necessarily useless, and you don't have to necessarily memorise when to use a certain representation. You can use them in lots of different scenarios. It's just that it's probably unnecessary in this scenario. You could also introduce a new representation for this one, though, of course, which is the Venn diagram. Again, you probably don't need it, but when you've shown that, it then leads into another subtle change on the question, which I'll show you now on the next slide. So So this question is subtly different to the previous one. We've still got our 65 Year 10 students, but this time they could study French and German. So these two things, these two languages, are not mutually exclusive anymore. The table might look a bit like that. It's not particularly nice. You could do a tree diagram. You'd have to think very carefully about how you do it though. So in this case, I've gone right. 65 students, French is 30 of them, therefore not French, I could work out. But then I've got German coming off that. So German, there's the 5 students that do German as well are part of those 30 students who do French. So you could do a frequency tree here. This is where the Venn diagram comes into its own, however, because we have that. And the Venn diagram, of course, lends itself particularly nicely to overlapping sets. So the thing here is that in comparison to question 3, 2 questions ago, where we had years 10 and 11, in that question we had 2 ways of splitting our set. We split them by year group and we split them by language. Now we are only doing it by language. So there's only one characteristic, if you like, that's splitting the group. And there's overlap, and that makes it suited to a Venn. But it's not that the others can't be done. And again, it's quite useful to introduce diagrams as being better than certain others because we've maybe reached the limits of certain others. So we have this kind of, I've done this here to try and demonstrate to you where certain diagrams are useful. We can see the 2 broad sections here are one trial. So if we look on the first 2 columns there, where just maybe one person is chosen, for instance, out of a group of people. If we only have one category, like they're split up according to the language they study, and that category can be mutually exclusive or not, then a Venn is probably the best choice. However, if we have 2 categories, such as they are split up by language they choose and year group they're in, then a better choice would be a 2-way table or a frequency tree, and both of those are equally as useful as each other. When we have 2 trials, however, this is now on the last 2 columns there, so for instance something like a coin followed by a spinner or 2 counters pulled from a bag, that's when probability trees come into their own. And that's when they become most useful. So we can see that they work for independent events, such as, a coin and a spinner, or 2 coins, or something, 2 balls taken out of a bag with replacement. Whereas for dependent events, conditional events, where we don't have replacement, probability tree is hands down the best option every single time. But we also have there our 2-way tables, which are good for non-numerical data, something like the 2 coins being thrown with heads and tails in the very first example I showed you. If your pupils are ready for a bit more nuance, actually you can use some other representations in certain cases. They're just not quite as useful. So for most pupils, you'll probably stick to when to use different tables when. Now the point of this is to show you that these things are not separate. These things are all very closely related, and we can make bridges from one idea to the next. And we can motivate one idea by coming to the limits of the previous idea and going, oh, now we need something new. If I may, I want to take a moment to highlight how drawing connections within a topic also then helps us to draw connections between topics as well. And that's the kind of thing we want to be doing as much as possible if we want our students to be able to solve difficult problems and non-routine problems, because we want them to see these connections. So here's a really good example. This was an Edexcel GCSE question from 2017. It was one of the first times we'd seen one of the new generation of difficult ratio questions. We've got a game with white shapes and black shapes, some are circles, some are squares, and then it's all about ratio. The point being, though, that we can still use a 2-way table. I can put the ratios of each of these into a 2-way table. So I've got colour, white and black down the left, and the shape, circle and square across the top. I've put the ratios, the first sentence about the ratio of the number of white shapes to black is 3 to 7. You can see that down the end column. But then I've put in the other ratios, 4 to 5 for white circles to white squares, and 2 to 5 of black circles to black squares. Now, of course, the 4 and the 5 across the top row don't add up to 3, but we know we can scale a ratio. So if I scale that ratio so that that part of it is worth 9, which the 4 and 5 do add up to, it's then easy to fill in the rest. You'll see my dodgy mouse writing now, because if that's 9, this must be 21. And to make the ratio 2 to 5, which does add up to 7, instead of up to 21, we need to triple both of those, so it becomes 6 and 15. And then we can answer the question because it asks what fraction of all the shapes are circles, and the circles are 10, all the shapes is 30, so we have 10 out of 30, or 1/3. Done. Now, that question was answered very poorly according to the examiner's report, and not many people tried to take the approach of a diagram like this. But when our pupils see that these diagrams are connected, and they see that when we have any scenario of a set of something that's characterised in 2 different ways, in this case colour and shape, then a two-way table is appropriate, then they are able to apply this and just extend it by adding in this extra concept of ratio. And I wanted to include that just to show you that the world of mathematics is so connected, and we should always be looking for ways to exploit the connections in order to make it easy for our pupils to grasp more of it. Here's our bridge again. We move pupils from their existing experience along the bridge through our carefully selected examples to get to the mathematical world, which is difficult for them to get their heads around at first because they're trying to enumerate concepts of unpredictability. And we work in that world for as long as we need throughout Key Stages 3 and 4, and then also into Key Stage 5, of course. And then once they have those tools, they will be equipped to go back the other way and apply them in the messy world. And they'll be able to do the things we spoke about at the very beginning, which is being able to have discussions about risk and to analyse unpredictability and to make decisions based upon multiple factors, because we've given them the tools to think about these ideas. I hope you found that interesting. There's the references there for the books and the papers that I mentioned if you want to look them up. Thank you very much.